Hi everyone, welcome to the algorithm course. In this video, I'm going to talk about the heap sort process. So in general, heap sort process will involve these steps. First, we need to arrange the elements in the max heap structure. And then we need to remove the tree root from the max heap structure and we put it to the sorted list. And then the final element of the tree is put to the root. And then we repeat steps 1 to 3 until all the elements are removed and sorted. Before we talk about the heap sort process, we need to understand some terminology. The first thing to talk about is a binary tree. A binary tree is a data structure such that each node except the topmost node has at most 2 children. So we can see the binary tree on the right hand side. We have a binary tree like this. We have the root being the element A, and from this root we can extend at most 2 children. So A can extend 2 children, B and C. And for element B, it can extend at most 2 children. So according to the binary tree structure here, we have only 1 child for element B, okay. And the line joining any 2 elements is known as a branch. And we can see the subtree indicated by the dashed boxes. So for another subtree on the right hand side, we can see that C is known as the parent node, and elements E and F are known as the left child and the right child respectively. And these 2 children belong to the parent, which is element C. And the next term to understand is the complete binary tree. A complete binary tree is a binary tree that is built from top to bottom and from left to right. So we can see the complete binary tree here. The first element to build is simply A, the second one is B, and the third one is C. And then we follow the top to bottom and left to right order to build the complete binary tree. So element J, for example, becomes the 10th element to be put into the complete binary tree. So we follow the top to bottom and then left to right order, okay. And a max heap structure that is used in the heap sort process is simply a complete binary tree with both left and right children being smaller than their parent. So now I have a max heap structure on the right hand side. In order to check the condition listed on the left hand side, we need to draw a lot of subtrees from this max heap structure. So for example, we need to check the subtree structure from top to bottom and from left to right. So we can see that for this particular subtree, 30 is smaller than 45, and also we can see from this subtree structure that 30 is smaller than 45 and 36 is also smaller than 45. It means that the left and right children are both smaller than their parent. So in this case, this subtree is a feathered subtree according to the max heap structure. And then we go to check another subtree using the top to bottom and left to right order. We see that 26 is smaller than 30, and at the same time 21 is smaller than 30. So we can see that both the left and right children are smaller than their parent. So we can say that the max heap structure is maintained in this subtree. Okay, we check another subtree following the top to bottom and left to right order. For this subtree, 19 is smaller than 36 and 28 is also smaller than 36. So we see that both the left and right children are smaller than their parent. So this subtree follows the max heap structure. Now we are going to check this particular subtree. We see that 17 is smaller than 26, and of course 14 is also smaller than 26. So both the left and right children are smaller than the parent. So this subtree follows the max heap structure. Now we are going to check the final subtree. So we can see that 10 is smaller than 21. So we can see that the left child is smaller than its parent. And for this case, we have no right child to check. And it is allowed because a max heap structure is simply based on the binary tree that can have one child. So let us see an example of the heap sort process. Suppose we want to sort these elements. The principle is to arrange the elements in the max heap tree structure first. So we take the first element from the unsorted list, and then we build the max heap tree first. And 65 becomes the root of our max heap structure. And then we are going to put the next two elements from the unsorted list to become the two children of the node that has a value of 65. But now we see that it is not a max heap structure because the children can be larger than the parent. So for example, in this case, 79 is already larger than 65. So even though 21 is smaller than 65, this max heap structure is not a correct one. So even though 21 is smaller than 65, we cannot really form a valid max heap structure. So in this case, we have to do the swapping between 65 and 79. After the swapping, we can see that the max heap structure can be maintained. So in this case, both the children are smaller than the parent. And then we are going to put two more elements to the max heap structure. And after we put these two elements, we need to check whether the max heap structure is still maintained. When we put 43 and 12 to the node that has a value of 65 according to the top to bottom and left to right order, we can see that this subtree maintains the max heap structure because 43 is smaller than 65, and at the same time 12 is also smaller than 65. And the final two elements are put to the max heap structure so that we follow the top to bottom and left to right order. So after we put 35 and 58, we see that the max heap structure cannot be maintained because the children are larger than the parent. So 35 is now larger than 21 and 58 is also larger than 21. So in this case, we have to do the swapping between the parent and one of the children in order to maintain the max heap structure. So now we can simply swap 21 and 58 such that the max heap structure can be maintained. Okay, the max heap structure has been created, and then we do the real sorting. So the first step of sorting is to move the root to the sorted list. So initially we had 79 being the root, and now we put the root to the sorted list, which is put at the end. And then we put the last element of the max heap structure to become the root. So initially the last element was 21, but now it becomes the topmost element, which is the root. And after this shifting of the elements, we see that the max heap structure cannot be maintained because we see that the children are larger than the parent. So 65 is larger than 21 and 58 is also larger than 21. So we need to do the swapping. Yes, after we swap 21 and 65, we can still maintain the max heap structure such that the parent is larger than both children. And after this swapping, we need to check another subtree following the top to bottom and left to right order. So for this particular subtree, we see that the max heap structure is not maintained because the children can be larger than the parent. So now we have 43, which is larger than 21. In this case, we need to do the swapping such that the parent is still larger than the children. So we swap 21 and 43 to maintain the max heap structure. Then we check another subtree following the top to bottom and left to right order. So for this subtree, we see that the children is smaller than the parent. So 35 is smaller than 58. In this case, the max heap structure is maintained. So after maintaining the max heap structure, we remove the root and put the root to the sort list, which becomes the second last element in the sorted list, and then we put the last element in the original max heap tree structure to the first element in the max heap structure, which becomes the root. And we check the max heap structure again, starting from the topmost subtree. So we see that this particular subtree is not following the max heap structure because the children can be larger than the parent. So 43 is larger than 35, and also 58 is also larger than 35. We need to do the swapping so that the parent is larger than both children, so we can swap 58 and 35 to maintain the max heap structure. And then we check another subtree following the top to bottom and left to right order. For this subtree, the max heap structure is maintained because the children are smaller than the parent. So we have 21 being smaller than 43 and 12 being smaller than 43 again. And after that, we can put the root of the max heap structure to the sorted element, which becomes the third largest element in the sorted list. And then we put the final element from the original max heap structure to the root position. And then we check the max heap structure again for the very top subtree first. It is not a max heap structure because the parent can be smaller than the children. So now 43 is larger than 12, and at the same time 35 is also larger than 12. When we do the swapping in this way by swapping 12 and 43, we can again maintain the max heap structure so that the parent is always larger than both children. And then we check another subtree following the top to bottom and left to right order. It is not a max heap structure because the child is larger than the parent, so we have 21 being larger than 12, which is not our goal of maintaining a max heap structure. So in this case, we need to do the swapping so that 21 becomes the parent and 12 becomes the child. So now the max heap structure is maintained for the entire tree, okay? And after the swapping mentioned previously, we need to check again the very first subtree to see if the max heap structure is disrupted or not. So according to the subtree here, the max heap structure can still be maintained after the swapping between 12 and 21. Why? Because the children are still smaller than the parent, so we have 21 being smaller than 43 and 35 being smaller than 43 again. So in this case, we can move the last element of the max heap structure to the sorted list, which becomes the fourth largest element. And of course, we need to put the final element of the original subtree to the root position. And then we check the max heap structure again. For this particular subtree, we don't have a max heap structure because the children can be larger than the parent. So 21 is larger than 12, and at the same time 35 is also larger than 12. So in this case, we need to do the swapping so that 35 becomes the root and 12 becomes the child. In this case, the max heap structure can be maintained. So after maintaining the max heap structure, we can put the root to the sorted list and the last element from the original max heap structure to the root. So in this case, 35 becomes the fifth largest element in the sorted list, and the max heap structure has only 2 elements left. Now we need to check whether we can still maintain the max heap structure in this case. But we can see that the child is now larger than parent. So 21 is larger than 12. So now we need to do the swapping so that 21 is larger than 12. And 21 becomes the parent and 12 becomes the child. And after the swapping, we are able to put the largest element in the max heap structure to the sorted list, which becomes the 6th largest element. And we are going to put the final element of the original max heap structure to the root position. And since we have only one element being left in the max heap structure, we simply put that element to the sorted list. In this case, all the nodes are in the sorted list already. and of course the sorting process is now complete. Thank you for walking through the algorithm with me. If you have any questions about the video, please leave your questions below the video. If you like this video, please give me a like and please subscribe to my channel. Thank you for watching.